All right, so I think we can begin slowly. I have started the streaming and I have also pasted the links in the chat as well as in the calendar also. Okay, so you can access them later. So today is a big day. We are going to revise week 5 and 6, which will be helpful for our quiz 2 preparation. In this particular session, we will be revising week 5 and 6. And on Friday, we have one more session at 10 a.m. In that session, we will revise week 7 and 8 along with the mock. If you have any doubts in the mock, you can ask them. Okay. So let's begin. As this is a revision session, we will not be covering each and every concept in detail. Rather, we will try to see which are important concepts that to be revised first and then solve problems around that and move on to the next topic. Okay. So before we begin, I would like to comment few things on quiz 2 question paper. So the syllabus for quiz 2 is weeks 5 to 8, not week 1 to 8. But as you all know, week 5 is differentiability and derivatives, which actually requires the concept of continuity and limits. So even though we didn't mention that the syllabus is not from week 1 to 8, internally we have to use the concepts that we have learned from week 1 to 4. Okay. So the syllabus is week 5 to 8. And again, the total marks and the total time you are going to get are the same as quiz 1. And the pattern will also be similar to quiz 1. So we'll have only two straight questions, each carry 4 marks. It can be either MCQ, MSQ, and AD. And then you will see 3 easy comprehension type questions, which carries 4 marks. So you'll have 2 subparts with 2 marks each. And then 4 medium comprehension type questions, which I say they are also easy, but quite time taking. Okay, so comparatively, 5 marks questions take more time. Okay, so if you know math, you can easily see, you can easily guess the number of questions that are going to come in the exam, as well as the total marks will sum up to 40. Everything is all set. Okay. So few things to get a good or reasonable marks, better marks in quiz 2. Okay. Few things that you should definitely follow are try solving the mock test that has been shared to you guys on your own. Okay, so this is very important because you may get the solutions from your friend and you may by heart them, but the problems that you are going to see in quiz 2 will not be direct taken from mock. Okay, so they are kind of replicas. So unless you know how to solve the problems in the mock on your own, you can't do it in quiz, right? So you don't have option to copy in the quizzes. So that is one thing. And try to attend or follow up later. Follow up on the concepts discussed in revision sessions. So all I mean is try to attend the revision sessions. And mainly you should not take the problems that I solve or so you should not take that. Rather you should take the concept that we are dealing and try solving more and more problems around that concept. Okay. So that is one thing. And finally, practice more problems related to the concepts concepts that are discussed in the revision sessions. Okay, so these are few things that you all have to do to boost your scores. Alright, so this is about quiz 2. Let's come back to the main agenda of today's session. We are going to revise the concepts of week 5 and 6, and here are the important concepts that are there in week 5 and 6. Okay, so you should know what a derivative is and what's the definition of a derivative, its denotion, and what is differentiability of a function. And then you should know differentiation rules. And slowly, once you understand these things, there is a concept where these derivatives are used, which is linear and quadratic approximations. Okay, so with that, week 5 gets ended. So these 3 topics cover week 5. And then more applications we'll see in week 6. Right, so you should know how to find the local maxima and local minima of any given function. Right, so what are the conditions for local maxima, conditions for local minima, and how do we compute them? Right, so that is one application, and then we slowly see little abstract theorems like Rolle's theorem and mean value theorem, which will help us to understand the Taylor's theorem, and then our very own favorite L'Hopital rule. So these are all applications of derivatives, and these will cover week 6. Okay, so we'll start with week 5 and then slowly move to week 6. Okay, so what is derivative of a function? So a function f is said to have a derivative value capital L at a particular point x naught if the following limit exists. Right, so if the following limit h tends to 0, f of x naught plus h minus f of x naught divided by h, if this is giving me values capital L, then I say the function f has a derivative value capital L. And this, once this exists, then it is denoted as f prime of x naught. Right, so this is the denotion of the derivative of a function at a point x is equals to x naught. So f and some 1 is there on top of it, on top of f1. F x naught is the denotion of a derivative, and which is equals to this following limit value. So we have to compute this limit and see whether the limit exists first. If limit does not exist, then we say derivative will not exist at that particular point, x is equals to x naught, right? So since this is a limit, there is always an existence that you have to check whether that limit exists or not. Right, so how do we check that? For checking that, all we have to do is we have to check what happens when h approaches 0 from the left hand side. We compute this slope. So this is kind of like slope, right? Whether this slope is equals to when I approach from the right. So the right slope and the left slope, both of them should be equal. So if both of them are equal, then those two are equal to f prime of x. Okay, so if f prime of x naught exists, then f is differentiable at x is equals to x naught. And if f prime of x naught exists for all x belongs to in the domain of the function, then f is said to be a differentiable function. Okay, so I hope this is just a recall. We have seen this in week 5, right? Let's do, or let's solve this problem real quick. Okay, so we'll use the definitions of derivative. You can also solve along with me. Right, so f of x is given to be x cube, and all we have to do is find the derivative at x is equals to 1. Right, so now x naught is 1 because we are interested at point x is equals to 1. Right, so all I have to do is I have to check this limit. H tends to 0, f of x plus x naught minus f of x naught plus h minus f of x naught divided by h, right? So now this is f of x naught plus h is nothing but f of 1 plus h minus x naught is 1, so f of 1 divided by h. And this will be limit h tends to 0. F of x is x cube. So f of 1 plus h will be 1 plus h whole cube minus f of 1 is 1 cube divided by h. Limit h tends to 0. 1 plus h whole cube, I can expand that. 1 plus 3h square plus 3h plus h cube minus 1 whole divided by h. Right, so there will be some cancellations. And then even h also you can cancel in the denominator and the numerator. Right, so finally we'll have this thing limit h tends to 0. 3h plus 3 plus h square. Right, so this is just a quadratic expression. So we know quadratic expressions are very smooth. They don't have any discontinuities. So I can directly substitute h is equals to 0 in the given expression. Right, so if I directly substitute h is equals to 0, there is no difficulties in substituting, so we can substitute. So we'll get 3 as the answer. So f prime of 1 is 3, and that will be the derivative value at x is equals to 1. So this is how we compute the derivative at a point given any function theoretically, right? So in practice we won't be doing this long, right? Because we all know given a function I can compute the derivative function, which is another function coming from the previous function, right? So you know we have studied those things also. So that we will see now. Okay. So this is before we know the rules, techniques, before we understand computing derivative or seeing derivative as a function itself. Right. So this is before. So we have to compute these limits, and that limit value, whatever we get, will be the derivative value. But we can also see this derivative as a function. Alright, so if you have a function from R to R, and this derivative as a function is defined like this. So f prime of x is basically limit h tends to 0, f of x plus h minus f of x divided by h. So if it exists for all x belongs to R, then our f prime can also be treated as another function. Right? So for every input, we will have a fixed output, unique output, which will be the limit value. Therefore, that will also give rise to another function. Right? So quick examples are if f of x is x power 5 minus 3x cube, then it is a polynomial of 5 degree. Right? At every point you take, it will be smooth on the left hand side and the right hand side. Right? There will not be any sharp turns. So therefore, derivative exists at every point. So if derivative exists at every point, which is nothing but this limit value exists at every point. Hence f prime of x exists at every point. Therefore, f prime will be a new function from R to R, and that function we can compute using the derivative rules, right? But since we know for this particular function x power 5 minus 3x cube, we have its derivative function as, we'll take the derivative of x power 5, which is 5x power 4 minus 9x square, right? So this gives rise to another function, another input output relationship, right? For the second example, I think all of us know, even if I take the derivative, I'll have derivative function as e power x, right? Now, since this is a new function, this is another function where I can compute derivative of this function, right? So if I compute the derivative of this function, f prime of x and its derivative, which is denoted as f double prime of x, which will be taking, again, this f prime of x is a 4-degree polynomial, which will be smooth again. And if it is smooth at all points, derivative exists at all points. Therefore, the derivative function exists. And that will be equals to 20x cube minus 18x. Right. So again, f double prime of x is another function, and it's a 3-degree polynomial. So it is smooth at every point again, and its derivative exists. Right. So I can take this derivatives forever. But what we observe is after certain derivatives, so if you see the third derivative will be 60x square minus 18, and the fourth derivative will be 120x, right? It is just a straight line, linear relationship. And if I take derivative once again, fifth derivative will be x, sorry, will be 120, right? Now a constant. And if I take derivative of this constant function, the sixth derivative will be 0. So once this becomes 0, it's just a 0 function, right? So if it is a 0 function and you take the derivative of 0 function, you'll get 0 again, right? So even though you have flexibility to take infinite derivatives, but after a certain derivative, from the next derivatives, everything will be 0, right? So from here on, you compute any derivative, it will be 0, right? So these are called higher order derivatives, which are also quite important. Okay, so these are important when you see this Taylor's theorem, no? So Taylor's theorem actually uses these higher order derivatives at a particular point. So you should know how to compute the higher order derivatives also. Even in the second example, we can actually take derivatives, and we observe that even if you take 100, even if you see the 100th derivative of this g of x, you will still get e power x. So it will not converge or go to 0, right? Unlike the first example, the second example, all the consecutive derivatives, okay, so everything will be e power x. So if you take the derivative of e power x, you will get back e power x itself. So like this, even if you take the derivative 100 times, you will get back e power x only. Okay, so it will not go to 0. So there are functions where its derivatives will not converge to 0. So some derivatives, as you take derivative on derivative, it may increase also. So the function power may increase, complexity may increase also. Okay, so these are something about derivative as a function and higher order derivatives. And then we will see the important rules that we should know. The first and foremost will always be simple ones. So if I add two functions and take the derivative of it, it is same as taking the derivatives and add them. Right? So sum rule. Similarly, I can do for the difference. So if I subtract two functions and take the derivative, it is same as take the derivatives and subtract. Okay, so these are sum rule. And then the second one is the product rule, which is really important. Okay, and product rule is fg. You take the product of two functions and its derivative is equals to take the derivative of the first function, multiply it with the second function, plus take the second function and take the first function and take the derivative of the second function, their product, and add these two terms together. Okay, and strong note is this is not f prime of x into g prime of x. Just like how we added two functions derivative to be equals to the derivatives of the sum, this will not product and its derivative will not be derivatives product. Okay, so by now you should be comfortable with this. We have also seen the proofs for all these properties, right? You should not forget, but if you forget, then we can't award you marks. Okay, so that is about product rule, and we also have division rule and the composite rule, right? So f by g's derivative will be equals to g of x into f prime x minus g prime x into f of x divided by g of x whole square. And the only condition, added condition is, since g of x is coming in the denominator, it should not be equals to 0. Okay. So even the division rule, you can treat it as f into 1 by g. Right? F as one function and 1 by g as another function. And if you use the product rule to it, you will see that you will arrive to this big expression. Even if you forget this, you can get from this. Okay. And then comes the composite rule, which is if you have composition of two functions and you want to compute its derivative, it is like you treat the inside function as it is and take the derivative for the outside function and then product it with the inside function's derivative. So quick extension would be if I have composition of three functions, right? So it's called composite rule or chain rule. What will this be? If I have the composition of three functions and I want the derivative of it, anybody?
It will be f prime of composition of g h of x, then it will be g prime h of x, then h prime of x. Yes,
Very
sir.
good. So that is why this is called chain rule, right? So even if you have some four composition of four functions, all you have to follow is like order or a chain. So you take the first derivative, keeping everything else inside it as it is, and multiply it with the second function's derivative and keeping everything inside as it is, and so on. Right? So these are some rules which we can use to compute derivatives of some other new functions. Okay, which are generated as a sum or product or by dividing two functions or these compositions. Right? And these compositions are also really important.
Sir,
Yes.
sir, the bracket over the outermost function, you missed it, sir.
Sorry, where did I? Where is it?
The outermost function, f.
So h of x, g of x. Ah, okay. Yeah, thanks.
Okay, sir.
Yeah, so the product rule and the chain rule are really important, and you can expect more problems related to that. Right, so those are slightly trickier. So therefore, you have to practice more and more problems around these properties. Okay, so let's do problems again. All right, so just on how to use these differentiation rules. Right, so we have given f of x to be x, g of x to be 2 by x. We asked f plus g functions derivative at a point 2 and fg's derivative at point 2. It's not point 2, it's at point 2. X is equals to 2. Okay. So for f plus g's derivative at 2, we can compute f's derivative at 2 and then add it with g's derivative at 2. Right, f of x is x. So f of x or function f's derivative is a constant 1. Right, so therefore, maybe we should compute them first. Okay, so if f of x is x, then f prime of x is 1. Similarly, g of x is 2 by x. So g prime of x is minus 2 by x square. Am I correct?
Yes, sir.
Okay, so once we have f prime of x and g prime of x, all we have to do is substitution. So we need f prime of 2 and g prime of 2. F prime of 2 is 1 plus g prime of 2 is minus 2 by 2 square. This will be 1 minus 2 by 4, which will be half. Very nice. If I want fg's derivative at 2, I can use the product rule. Right, so I know f prime of 2, which is 1 into g of 2. So g of x is 2 by x, so it will be 2 by 2 plus f of 2. F of x is x, so f of 2 is 2 into g prime of 2. So g prime of 2 is minus 2 by 2 square. So you can see 1 into 2 by 2 is 1, 1 into 1 is 1. And then here we can see 2 into minus 2 minus 4 divided by 4. So it will be minus 1, which will raise to 0. Okay. So I would like to state a quote here. Okay, so if you want to chop onions, all you need is a small knife. And you don't need an axe or something. So here if you carefully observe this f of x and g of x, and if you had seen the product function, okay, so what is f of x into g of x?
2.
It is simply 2, which is a constant function. And if I take the derivative of a constant function, it will be 0 at any
0.
point. Right? So now you should not run behind formulas every time. Okay. So just take a minute, take not a minute, at least 10 seconds before you use the formula. You can use the formula. I'm not denying that formulas will lead you to wrong answers. Formula actually gave us the correct answer only. But before you use the formula, just take a 10 seconds stare at the question. Okay, so do I really have to use the formula, or is it much simpler than using formula? Is there any way? Right, so here if we stare at two functions, the product function is just a constant function. So once it is constant function, if I take the derivative of it, it will just simply be 0. So it's like you don't even have to solve for it. Okay. So that is the suggestion I wanted to give, not only for this problem, so in general, your quiz 2 also. So before directly jumping to the solution, just identify which method should I use so that I will get to the answer real quick. So for that, you need more and more practice, and that's how you get the experience of what technique to be used. Okay. All right. So let's move to the next problem. So we have given f of 1, g of 2, f prime of 1 and g prime of 2. And we have asked you to compute g of f of 1's derivative minus f of g of 2's derivative. Right. So for that, we just have to use the chain rule formulas. G of f of 1's derivative will be g's derivative f of 1 into f's derivative at 1. Right. And f of g of 2 derivative will be f prime of g of 2 into g prime of 2. That's it. We know f of 1. Substitute f of 1, which will be g prime of 2 into f prime of 1. And this will be f prime of g of 2 is 1. So this will be f prime of 1 into g prime of 2. So both are same actually. When I take the product of this g prime of 2 into f prime of 1, so g prime of 2 is 4 into minus 5, which will give me minus 20. And here also it will be minus 5 into 4, which will be minus 20. Now I have to take the difference of this 2. So if I take the difference of these two, what will I get?
0.
0, right? So all I have to do is taking the difference. I take the difference. I'll get minus 20 plus 20. It will be 0. Yeah. So again, here also, all you have to observe is this is same as this. If two things we are subtracting where both are same, it gives rise to 0. And again, strong note, okay. So here in our revision session, we are getting zeros doesn't mean that in quiz there will be high probability of having answer 0. Okay, so don't assume things. Okay, so solve it, and then if you truly get it, then it's okay. All right, so let's move to the next problem. I think this problem you would have also seen somewhere, and it's a nice problem related to this kind of concepts. Okay, so we have been given a relationship which involves some understanding of our function f, which is f of x plus y is actually equals to f of x into f of y for all x, y. Okay. And f of 9 is 3 and f prime of 0 is 8. All we need is find the value of f prime of 9. Right. So we really have to use all the techniques that we know to solve this particular problem, and also the knowledge on the expressions. Okay, so we have f prime of 0. We have given f of 9. All we have to do is to find f prime of 9. So f prime of 9, if I write it in the limit definition, f prime of 9 can be f prime of 9 will be equals to limit h tends to 0 f of 9 plus h minus f of 9 divided by h, right? So why I have written in this fashion, because I know I can use this f of 9 which is given in the information, but f prime of 0 is also given. If I can pull in f prime of 0 somewhere to solve this to solve for f prime of 9, then our job is done, right? So for that, what I will do is I can write this f of 9 plus h. So you see, f of, in place of x you put 9 and in place of y you put h. You'll see that f of 9 plus h can be written as f of 9 into f of h, right? So that's how the function behaves, minus f of 9 divided by h. So if I pull out f of 9 for common from the numerator, this will be limit h tends to 0 f of h minus 1 divided by h, right? So we have reached till this point, and we also know, similarly we also know f prime of 0 is actually limit h tends to 0 f of 0 plus h minus f of 0 divided by h, and this is limit h tends to 0 f of h minus f of 0 divided by h. If you stare at these two expressions, this one and this one, most of the things are common, but there is only one difference, right? So that difference is, here we have 1, here we have f of 0. So if I can prove that f of 0 is 1, then these two expressions are the same, right? So for that, we need f of 0. Somehow we have to find f of 0, right? And see whether f of 0 is 1 or not. So for that, we'll just go back to the expression that is given, the equation that is given, which is f of x plus y is f of x into f of y, right? So you just substitute x is equals to 9 and y is equals to 0.
Yes, sir.
Sorry?
F of 9.
So since we know f of 9 value, we take one x to be 9 and y to be 0, or x to be 0 and y to be 9, both. You just substitute x to be 9 and y to be 0, right? So if you do that, what will we get? We'll get f of 9 plus 0 is equals to f of 9 into f of 0. And left hand side we have f of 9. So f of 9 equals to f of 9 into f of 0, right? And f of 9 is not 0. F of 9 is 3. So if you substitute 3 is equals to 3 into f of 0, we'll get f of 0 to be 1, which is what we require, right? So which is what we anticipated. And once f of 0 is 1, we can clearly see that this and this are equal. So if both are equal, I can simply replace this with f prime of 0. Right, so this will be f of 9 into f prime of 0. Right, so we know f of 9 and we also know f prime of 0. Therefore, f prime of 9 will be 3 into 8, which is 24. right? So that will be the answer. Any doubts? Anybody?
No, sir.
No, sir.
All right. So then let's move forward. Right. So practice more problems related to this usage of differentiation rules. Okay. So practice more problems around this and higher order derivatives also. Okay. So let's move to the next concept, which is called linear approximations. As the word itself says, term itself says that it's linear approximation. So we are going to approximate some function as or equal to a linear expression, right? And once we are approximating, it will not be exact, rather it will be an approximate value. Yes, Shashank? Shashank, do you have any doubt? They have asked to find f prime of 9. Yes. Yeah, that is what we found, no? That is where we started. And we wrote the definition for f prime of 9. And then we have arrived to this expression. And then we have involved this f prime of 0. And then we have also found f of 0. And we have used all of them to get to see that f prime of 9 is nothing but f of 9 into f prime of 0. Alright, so the linear approximation L of x, which is a linear equation that approximates any other function f of x around a particular point. Right, so the linear approximation L of x for any function f of x around x is equals to x naught is given by this expression. Right, in this expression you can see we need f of x naught, we need the value of the function at that point, and we need the derivative value at that point. So these are the two things we have to find to get the linear approximation, to find the linear approximation. Alright, so let's do an example. Given f of x like this, x square minus 1 by x plus 1. This is not polynomial function. This is not a rational function. This is a combination of, yeah, this is a rational function, right? And it's very hard to find the value of f of 0.1, right? Now in this generation, it's not hard. So think that we are in some 1500s or 1400s around. Okay. So at that time, we don't even have calculators. Okay. So at that time, if you want to compute something like f of 0.1, right, it takes some time to compute, right? All right. So for that, if we can come up with a linear function around this x is equals to x naught, x is equals to 0, then it's very easy for us to approximate the value. So for that, we use this approximation. Okay. All right. So let's see the example. F of x is given to be x square minus 1 by x plus 1. We have to find the linear approximation around x is equals to 0. Right. So for that, we need two things primarily. Right. So we need f of 0 and f prime of 0. Right. So we need these two things to find the linear approximation around x is equals to 0. So we have f of x, so we can find f of 0. F of 0 is 0 square minus 1 by 0 plus 1, which will be minus 1. Similarly, for finding f prime of 0, right, so we need f prime of x. F prime of x is 2x and minus 1 by x plus 1's derivative, which will be plus 1 by x plus 1 whole square. Okay. So once we have this, we can find f prime of 0, which is 2 times 0 plus 1 by 0 plus 1 whole square, which will be 1 plus 1. Right. So we have the required values minus 1 and plus 1. All we have to do is to substitute. So the linear approximation around x is equals to 0 will be f of 0 plus f prime of 0 into x minus 0. F of 0 is minus 1 plus f prime of 0 is 1 and x minus 0 is x. And this will finally be equals to x minus 1. You see, the linear approximation that we got was x minus 1. So x minus 1 looks really simple, no? Now you can compute L of 0.1. So 0.1 minus 1 will be minus 0.9. So we can do it in seconds. Right? So you see the expression of f of x and you see the expression of L of x. And what we claim that f of x and L of x behaves in the same manner around x is equals to 0. Okay, so that is why we use this approximations. Okay, so this is L of x. Alright, so that is linear approximation. For quadratic approximation, we will have one more term, which will be f double prime of x naught divided by 2 factorial into x minus x naught whole square. So quadratic approximation is like we are going to approximate a function in terms of a quadratic function. So once it is quadratic, we will have x square term coming into the picture. Right, so for quadratic is a better approximation, but the cost is you have to compute more compared to the linear approximation. For quadratic, we need f of x naught, f prime of x naught, just like for linear approximation. Along with these two, we also need f double prime of x naught. Right, so for that we have to compute f double prime of x, which is little time consuming. Right, so if you can spend that time, you will have much better approximations. Okay, so we will do that. So we already have f of 0 and f prime of 0. We also have f prime of x. So for finding f double prime of x, we have f prime of x as 2x plus 1 by x plus 1 whole square. Right, so from here, if I take the derivative once again, I'll get 2 minus 2 by x plus 1 whole cube. So you can check this, you will get this expression. Once we have this, we need f double prime of 0, which is 2 minus 2 by 1 cube, which is 2 minus 2, which will be 0. So that means once we have 0, I don't know why I got 0, why I came up with this expression. But even quadratic approximation is same as linear approximation in this particular example. Okay, if you compute q of x, you will see that 1 minus 1 plus 1 into x plus 0 by 2 factorial into x square, which will again give us x plus 1. Okay, so which states that for this function f of x is equals to x square minus 1 by x plus 1 around x is equals to 0, linear approximation is as equally better as the quadratic approximation. Okay, but this may not be true for every other example. Okay, so be careful about it. Here f double prime of 0 turned out to be 0, that is why we got the same expression. If double prime of 0 is something else, we'll have that term also here. Okay, I hope you all got the sense. All right, so that's about week 5. Okay, so we'll take a 5-minute break maybe. We'll resume at 5 p.m. Okay, so I just wanted to give you guys a break because we are dealing 2 weeks of content in one session. So it's very hard to intake. Okay, so we'll resume. So you all can have some water. Okay, go relax and come back by 5. Yeah, hope all of you are back. I'll resume now. Okay, so in week 6, in week 6, we have started with local maxima and local minima. How can we compute them using the idea of derivatives? Right, so here you can see a roughly given curve and some points where locally around that region it reaches the maximum value, and locally around that region it reaches the minimum value. Those are called local maxima and local minima. So here in this example, this point, this point, this point, all 3 points are called local maximas. Okay, because locally means to the left and to the right at every point. Right, so around that region, that point will attain the maximum value. If you move left or right, the function value will decrease. Right, so such a points are called local maximas. And contrarily, these 2 points you see are called local minimas. Right, again, why they are called local minimas? Around locally, left or right, if you move, the function value will increase. Okay, so this at these points, the function value will attain the minimum value around that region. There are some conditions and properties for these local maxima and local minima. Right, a point x is equals to a is a local minima if the derivative at that point is 0. Right, you can clearly see the derivatives at these points are nothing but the slope of these lines, right? So the tangents at these points will be parallel to x-axis. So even if it is local maxima or local minima, the slope will be 0. So that means the derivative at that particular point will be 0. Right? So once the derivative at that point is 0, that will be one condition for local minima and local maxima. Along with that, how do I differentiate local minima and local maxima? I will compute the double derivative and see the sign at those points. And can somebody say for local minima, my double derivative value should be equals to 0, greater than 0, less than 0?
It's greater than 0.
If it is greater than 0, it is local minima. If it is less than 0, it is local maximum. So only two things we have to compute. Right, so for computing local maxima and local minima, all we have to do is we have to compute or solve for f prime of x is equals to 0. So you have to solve this equation first, f prime of x to be 0. So we'll get some values, x1 here, x0, x1, x2, x3, x4. Right, so we'll get some values depending upon the degree of the polynomial. We'll get some roots. Then for commenting on local minima or local maxima, we will check the signs of the double derivative at these points. Okay, if it is greater than 0, then it's local minima. Less than 0, it's local maxima. And there is one more case also. It can be equal to 0 also. In those cases, this is called as a saddle point. Okay, so which is not local maxima, nor local minima. Okay, which is called a saddle point. So the best way to understand it is look at the curve or graph of x cube. So x cube at x is equals to 0 is the saddle point. Okay, it is neither local maxima, local minima, nor local minima, but these conditions will be satisfied. F prime of x will be 0 at x is equals to 0. And even if you compute f double prime of x, you will see that it will be 6x, which is again 0 at x is equals to 0. So such points are called saddle points. For now, we can move out our discussion from saddle point and let's focus on local minima, local maxima, and how do we classify them. Let's do an example. So let's consider a function f of x is equals to x power 4 plus 4x cube plus 4x square plus 15. It's a 4-degree polynomial. Right. So what they're asking is find all the local maxima and local minima points of f of x. Right. So how do we do this? As I said, first step will always be computing f prime of x or solving for x such that f prime of x is equals to 0. So for that we will compute f prime of x first. F prime of x will be 4x cube plus 12x square plus 8x. Right. So this will be f prime of x. If I equate it to 0 and if I pull out 4x common, I'll have x square plus 3x plus 2 is equals to 0. Right. Now x square plus 3x plus 2, I can factorize it. It will just be x plus 1 into x plus 2 is equals to 0. So if product of three terms becoming 0, at least one of them should be 0. Therefore, this implies either 4x is 0, which is nothing but saying x is 0, or x is equals to -1, or x is equals to -2. Right. So these are the 3 points where our f prime of x becomes 0. Right. And for commenting on whether it is local minima or local maxima, what we have to do for that, we need f double prime of x and its sign at x is equals to 0, x is equals to -1, x is equals to -2. So let's compute f double prime of x, which you can compute it from f prime of x. Take the derivative of f prime of x, you'll get f double prime of x. That will be 12x square plus 24x plus 8. Right. So once we have this, f double prime of 0 is 12 times 0 square plus 24 times 0 plus 8, which is 8, which is greater than 0. Therefore, 0 is local minimum. And then f double prime of -1 will be 12 times -1 whole square plus 24 into -1 plus 8. Right, if I compute this, 12 minus 24 plus 8, which will be -4, which is less than 0. Hence, -1 is a
Local maxima.
local maximum. And similarly, you can compute for f double prime. You can compute for f double prime of -2, which will be 12 into minus 2 whole square plus 24 into 2 plus 8. So now 12 into 4 is 48, 48 plus 48. So everything is positive here. We don't have to compute really. So you see that all the terms are positive, so it will be positive. Right? Since we only need the sign, you don't have to sit and solve for what value you get, right? So if I add 3 positive terms, it will always be positive. So that I know. So even here also, the first case also, first 2 terms are 0 and the last term has positive value. So it will be positive. Right? So minus 2 is local minimum. If I plot this, can I roughly plot this? Because I know where the function has local maximas and local minimas, I can actually roughly plot the function, right? Right. So the special points are at 0, -1, and at -2, right? And the expression I have was f of x is equals to, so I'm plotting f of x, okay? So I'm roughly plotting f of x after computing this local maxima and local minima. So this local maxima, local minima points help us to roughly plot the function. And I will tell you, once you are able to roughly plot the function, you know in which interval this particular function is increasing and in which interval it is decreasing. All these things we can comment. Right. So f of x we have is a 4-degree polynomial, which is x power 4 plus 4x cube plus 4x square plus 15. Right. So for plotting, all you need is the highest degrees coefficient. So if you stare at this x power 4 is a dominating term. Right. So because as x increases, x power 4 grows faster than any other term because it has power 4. Right. So if it is positive, it will dominate other 3 terms. And we can clearly see that as x increases, this f of x will also increase, and as x tends to infinity, it will go to infinity. Right. So what we do is, since 0, at 0, you can clearly see the value is 15. And that is the local minima. Right. So if it is local minima, around that x is equals to 0, left or right, the function value should increase. That means the function will look like this around these 2 points, around this point. And as x tends to infinity, we saw that this will go to infinity. Right. This will have minima. And at -1, we have maxima. So this will go like this, and till -1 it will just increase, and at -1 this will attains its maximum value, and left of -1 it will just decrease still till -2, and at -2 it will again increase. So this is a rough plot, this is not the exact plot, right? So once you have this kind of plot, right, you can clearly see, at least you will not be able to exactly plot the values, but you can clearly see that left of minus 2, from minus infinity to till minus 2, right? You can see my function values are decreasing, right? So as it's a decreasing plot, right? So the function is coming downwards, right? So if I start from minus infinity and if I slowly start approaching till minus 2, the function is decreasing. And from minus 2 to minus 1, the function is increasing. And from minus 1 to 0, it is decreasing. And from 0 to infinity, it is increasing. Yes, Nitish.
Sir, whole the graph is above the x-axis. Is it a, how we determine this is graph above the axis or sometimes
No, it
crosses the
won't be
axis?
above the x-axis. So that is what I said. It is rough plot. The function values we don't know.
Oh, sir, if we get the roots, then we can determine the accurate graph.
Yeah, if you know the roots also, then that will be an added information,
It will
right?
increase the efficiency of accuracy of the
Yeah,
graph.
it will increase the efficiency of the plotting. So if you have the roots also, that will help. But if you only have this local minima, local maxima points, you can actually comment on in which interval the function will decrease and in which interval the function will increase. So you cannot comment on the function values, whether
Okay,
it will be above x-axis or below x-axis. These
sir.
things we cannot comment. Okay.
Yes, sir.
Mhm. So this plot can be like this also. Like this, it will decrease. It will increase. It will increase, decrease, and it can come like this, and then it can grow like this also. So this can also be a plot. But what is common between black and red plot? We can see that till minus 2, the graph will decrease. And from minus 2 to minus 1, the graph will increase. And from minus 1 to 0, it will decrease. And from 0 to infinity, it will increase. This is what we can comment. Okay. So yeah, so this I wanted to mention it here. So you should know how to comment, how to find local maxima and local minima of a given function. And once you find the local maxima and local minima, then you can roughly plot, and or at least if you, even if you don't plot also, you can at least comment on in which interval the function is decreasing and in which interval the function is increasing. Okay, so that we can say. So in order to conclude that, what you have to do is you have to compute local maxima and local. So that's my point here. Okay. So let's go to another application and a few more theorems, which are Rolle's theorem and mean value theorem. Both are almost the same. The only difference is the following. Okay, so what Rolle's theorem states is you have a function f which is continuous and differentiable in the interval ab. Okay, so here is the interval ab. Right, so you know that f is continuous and differentiable in this interval. In this region, there is the function, but we don't have the information about the function. What we know is it is continuous and differentiable. And what we also know is the function value at a and function value at b both are same. Okay. So then what this Rolle's theorem states is there exists a c in between such that f prime of c is a local maximum or local minimum. Or in other words, f prime of c is 0. Okay, so once we know that it is continuous and differentiable, all it could be possible is it can be like this, it can be like this, it can be like this, right? In whichever way you connect these two curves, these 2 points smoothly, because differentiability is also there. So they should be smooth. In whichever way you connect, you can clearly see that there will always be a point where you change the direction. right? So you are at f of a, the function value, and if I move up, I should come back to that same value. If I move down, I should again grow back to get the same value. So that's the understanding. Okay. So that means there will always be a turning point or local maximum or local minimum. So that is what Rolle's theorem states. What does mean value theorem state? This is a slightly next version of Rolle's theorem. We kind of leverage the condition of being f of a being equals to f of b. Okay. So what we have is we have the same interval. Okay. So same interval AB. And we also know that our function is continuous and differentiable in this AB, interval AB. Okay. But the only condition we don't have here is f of a may not be equals to f of b. So it can be somewhere. All we are saying is no matter how you connect these two now, right? So in any way you connect smoothly, then all we are saying is if you draw a straight line connecting these two, okay, you draw a straight line connecting these two. I know it won't happen. Okay. So if you draw a straight line connecting these two, now what mean value theorem states is no matter how you connect these 2 points, there will always be a point. Okay, so there will always be a point where when you compute the slope of that particular point, slope is nothing but the tangent line slope, right? So that will be equals to the slope of the line joining these two. Okay, or you just tilt this. You just tilt this such that this line becomes a straight line. Then use Rolle's theorem. That's it. That is what it is saying. Okay. So f of b minus f of a divided by b minus a is nothing but the slope of this straight line. Slope of this straight line. Right. And this mean value theorem states that no matter how you connect, there will always be a point C when I compute the derivative value or the slope at that point, which is equals to the slope of this straight line. That's it. Okay. Yeah, Nitish. You're on mute.
Yeah, is it fine, sir?
Yes, yes.
So according to Rolle's theorem, if the all conditions satisfy, which is mentioned here, then there is a C between A to B where f dash C of 0. Let's suppose if the missing graph between A to B is a straight line, then we can say there's an infinite many points where f dash of C is equal to 0.
Correct. So all it says is there will exist one point at least where f prime of C is 0. Okay. It's not exactly one point.
No,
It is
if
at least.
if the missing graph is a straight line, then there are infinitely many C's where f dash of C is equal to 0.
Yes, there will be there can be a possibility of having infinitely many values for C. You are correct. There can be two values also. So if the curve is like this, at this point it attains at this can be a C and this can also be C. There can be the connection can be like this also. So here you can see there are many more possibilities for C. Okay. So this Rolle's theorem and mean value theorem states is there will exist at least one point. At least. Okay. I hope that is clear.
Yes, sir.
All right. So that's about Rolle's theorem and mean value theorem. If possible, practice few practical problems like, speed, distance. So when you start from your home and you're reaching your college or office, you will not travel at a constant speed, right? So at start you will be 0 and slowly you will raise the accelerator and the speed will increase. And if the road is clear, we may touch 100 km/h also. And then by the time we reach college, we have to slow down and we'll come to an halt. Right? So if you compute the average speed, it could be some 43 or 45. Right? So that average speed 45, at least one point of interval you would have touched 45. That's what mean value theorem states. Okay. So average value is attained at least at one point in between. Right. So that is mean value theorem. Okay. So now let us come to our favorite rule, which is L'Hopital rule. We started using this L'Hopital rule from week 3 itself. Right. So many of us used this L'Hopital rule in sequences, where we shouldn't use them. But we kind of fascinated about this rule and we have been using it. But here is the time we can use L'Hopital rule perfectly. Okay. So what this L'Hopital rule states is, if you are trying to compute the limit of rational functions, f of x by g of x at a particular point. Okay. So when we try to substitute that point, we might end up getting expressions like 0 by 0, infinity by infinity, or minus infinity by infinity, or infinity by minus infinity. Right? These are all called indeterminate form. Right? You can't determine the value exactly. I hope all of you know this. These expressions are called indeterminate, like indeterminate forms. So when we are arriving to these kind of forms, we cannot exactly say what value will it be. So for that, what this L'Hopital rule says is, if f of x and g of x are differentiable functions, then you differentiate the numerator, you differentiate the denominator, and then compute the limit, which will be exactly equals to the limit of the function at x naught for f of x by g of x. Right? So that is what L'Hopital states, and that's not the beauty. The beauty is you can use this L'Hopital as long as you get these indeterminate forms. So that means even if f prime of x and g prime of x giving you 0 by 0 form, then you can further use L'Hopital right, and you can use them indefinitely. Right? There is no stopping. You are getting 0 by 0, use L'Hopital. You are getting 0 by 0, use L'Hopital. Okay. So yeah, all it states is when you arrive indeterminate forms, L'Hopital rule helps us. You take the derivative of the numerator, take the derivative of the denominator, and then compute its limit at that point. It is same as the limit of the earlier expression. Okay, so here are some examples. So we see if we directly substitute, we'll see what happens and then we'll come back. So this is 0 cube divided by e power 0 square minus 1. We can see that we will be arriving 0 by 0 form, right? And then we can use L'Hopital by L'Hopital rule. What I can do is I take the derivative of the numerator. The derivative of the numerator is 3x square divided by derivative of the denominator. So you have to be a little careful here. E power x square is composition of two functions. Right. So when you take the derivative, you have to take it carefully. It will be 2x into e power x square. Right. So now there will be some cancellations and the expression would be limit x tends to 0, 3x by 2 into e power x square. Now you should not rush taking L'Hopital rule, okay? You cannot do one more, you take the derivative of the numerator, take the derivative of the denominator and proceed. You should not do that. Before that, there is a checking process, right? So again, you have to check whether you are getting 0 by 0 form or not here. So if I substitute x is equals to 0, what we get is 3 times 0 divided by 2 times e power 0 square, which we get 0 by 2 times e power 1, e power 0 is 1. So we are getting 0 by 2, which is 0. Right, so we got the answer, we didn't get any indeterminate form, we got a determinant value, which is 0. Therefore, the limit of this expression, the value of this expression, let me see. Okay, so similarly, you can compute for the second problem also. So second problem also, if you try to substitute -2, you will see that you will end up getting 0 by 0 form. Therefore, you have to use L'Hopital rule. Take the derivative of the numerator, which will give us 3x square divided by 5x power 4. Then you will cancel, and it will be 3 by 5 into x square. And I can freely substitute -2. There is no harm. Right, so we'll end up getting 3 by 20. Alright, so you are free to use L'Hopital rule as long as you get 0 by 0. Okay, so don't use L'Hopital rule to simplify numerator and denominator. Okay, so that's a strong note. I have seen many of your earlier friends or seniors, you call it, they will use L'Hopital rule for everything. No matter, they won't even check for 0 by 0. You see a rational function, they are asking you to compute the limit value of a rational function. Use a L'Hopital rule to simplify the numerator and denominator. You use it multiple times such that the numerator and denominator gives you constant values. There you stop. Okay, so at least I hope you guys won't do the same mistake that your seniors has done. Okay, so that's a strong note with respect to L'Hopital rule. Practice more and more problems around this L'Hopital rule also. All right, so let's come to our final topic, which is Taylor's theorem. And again, as quiz 2 is a time-bound exam, right? So Taylor's theorem of higher order, it's very time-consuming, right? So you have to compute more and more derivatives at a particular point. For that, you have to compute more expressions. So that is why, at least for quiz 2, practice problems related to linear approximation and quadratic approximation at max. Okay, so don't sit on solving Taylor's theorem for some sixth degree or 7th degree. Okay. What does this Taylor's theorem states is, it actually gives us the approximation along with the error bound, right? So that's the beauty of this Taylor's theorem. Okay, so it will give us the approximation. So this we have seen earlier, week 5, right? In the week 5. So this is just the linear approximation. F of a plus f prime of a into x minus a. This is the linear approximation of this function f of x. And the next term, the third term, which is what we call as error term. Right. So if you remove this error term, it will be an approximation, not exact. So f of x is approximately L of x, not equals to L of x. Whereas here, you can see we are using equal to. So f of x is actually equals to the linear approximation plus the error term. And this error depends on the approximation. So how close we are to the actual value. So the difference is what error is. Okay. So for finding, for any problems, there can be two types. One, we ask you for the approximation, and another we ask you to bound the error. So for bounding the error is basically f of x minus L of x. Right. So here you can see from the expression itself, error is mod f of x minus L of x, which is this mod x minus a whole square. Right. And this x2 is not known to us. X2 is some point. Okay. Now I can bound this value by its maximum value. So the maximum value that I can attain with this attain for this x2 in this interval so everything else will be lesser than the maximum value only. Right. So this is the maximum error that can be possible. So again, error for error also, we can't find the error exactly. Rather, we will try to find the maximum possible error. So that is why in problems also you would have seen, you would be asking about the maximum possible error, right? So for maximum possible error, you have to find the maximum value for of this expression f double prime of x2 divided by 2 factorial into x minus a whole square, where f double prime of x2 is a function in terms of x2. For finding the maximum value, we know, right? So how to find the maximum value? You take the derivative, equate it to 0, and then you'll find the maximum value in that interval. Right? So let's do an example to understand this. So ln x is log base e of x. Right? Even if you don't know what ln x is, that is okay. We are concentrating ln x in the interval 1 comma e. So all you have to know is how the curve looks. Okay, so let me plot the curve for you guys. So ln x in the interval 1 to e will look like this. Okay, ln 1 is 0. And as x increases till e, the function ln e is 1. Okay, so and this is how a rough plot will be like this. Okay, so this is what you need, and you need the derivative also, right? So for that, if f of x is ln x, the derivative function will be 1 by x. Okay, so once you know 1 by x, once you have 1 by x, the derivative of 1 by x, we know how to compute. Right, so this is f of x for us, and we were asked to find a degree 1 polynomial, which is L of x. That means they are asking us to find the linear approximation to approximate f of x in the interval e comma x. So we have been given the function till e, and they were interested in approximating this function in this interval. So e to x. So what happens to the function after e? For that, they asked us to give a linear approximation. So for that, what we will do? We will find linear approximation. We'll find linear approximation around x is equals to e. Right, so that is what we can do. For that, I need f of e and f prime of e. Right, so we need these two. f of e is, we have already, f of e is 1. Right? For f prime of e, as I gave you, f prime of x will be 1 by x, which implies that f prime of e is 1 by e. So once you have these two things, I can compute L of x. So L of x is simply f of e, f prime of e into x minus e. Right? So if I substitute 1 plus 1 by e into x minus e, we'll get 1 plus x by e minus 1 by e into e, which will give me 1. This and this will get cancelled out. We'll get a straight line with slope 1 by e. So L of x is x by e. Right, so we have L of x, which is a linear approximation for this function f of x around x is equals to e, and that is what they asked in part 1. In part 2, using Taylor's theorem, find the maximum possible error. You see, we are not asking the error, rather we are asking find the maximum possible error in f of 2e minus, like, the difference between these two at point 2e. Right, so part 2, they are asking to bound f of 2e minus L of 2e. Right, so this is bounded by maximum possible value for x2 in the interval e to x, right, and f double prime of x2 divided by 2 factorial x minus a whole square. Right, so a is again e here. Right, so that is where we found the linear approximation, and here x is, so you see f of x minus L of x is bounded by, so whatever x you take here on the left hand side, that is what the x value. Right, so here we are interested in f of 2e minus L of 2e. Therefore, this x will be 2e. Right, so the right hand side will only be in terms of x2. So everything else will be given or known to us. Okay, so now all we need is to find the maximum value of this expression. Right, so for that we need f double prime of x. We already have f prime of x with us. If I find f double prime of x, will be 1 by x derivative, which is minus 1 by x square. Correct? And if I take the absolute value, this will just be 1 by x square. So now what I want to find is maximum value in the interval e to 2e, right, for this expression 2e minus e whole square. Right, so I want to find this. For this I will substitute what all I know. So f double prime of x2 is 1 by x2 square divided by 2 factorial. 2 factorial is 2 into 2e minus e is e square. Right, so I can pull out this e square, 2, everything out because they are all independent of x2. So I'll have e square by 2 into the maximum possible value in the interval e to 2e for the expression 1 by x2 square. Right. So if you look at the expression 1 by x2 square as x2 in the interval e to 2e, how does 1 by x2 square behave?
Decreasing.
It will decrease, right? So if I take x2 to be e, I'll have expression value to be 1 by e square. And as I increase the value of x2 is in the denominator and greater than 1. So that is what you have to observe. So as x2 increases, one by x2 square value decreases. And I need the maximum value, maximum possible value. So where will the maximum attain?
E.
At E in this interval. We only concentrate in
Yes,
this
sir.
interval.
Yes, sir. In this interval, we'll get the
this
maximum
interval,
value at
yeah,
E.
At E. So therefore the maximum value, this will be lesser than or equals to, or this will be equals to, the maximum will be attained at E. Any other value, the value is lesser than 1 by E square. So therefore this will just be 1 by E square. And this will get cancelled out. And we'll get half as the, half is not the error, half is the maximum possible error. Maximum possible error at point 2e. Okay, so this is how we compute the maximum possible error. Okay, so there are two ways to ask this, right? So either we ask you the linear approximation or we'll ask you to bound the error. Or in other words, we ask you to give the maximum possible error. Yes, Nitish.
Sir, if we have absolute maximum error, then how shall we decide that that absolute maximum error should be added or subtracted to enhance the accuracy of value?
Sorry, can you restate your question?
If we have the maximum absolute error, then how shall we decide that error should be added or subtracted to enhance accuracy of value?
Okay, so that you cannot say, no. Once you are taking absolute value, all we are saying is we are not worried whether to add or whether the error is lesser or higher. We are not worried about it. Error is an error, right? So if I want the function value, I should get the function value exactly. Even if I am getting more or less, both are equal to me. That is why we have this absolute value, absolute coming into the picture. Okay.
So there's no need to add or subtract the error.
There is no need to add or subtract. We are not worried about whether the error is more or less.
We can just show the error. We can okay, sir.
So that is why we had this absolute coming into the picture. Okay.
Okay, sir.
All right. So even the quadratic approximation also we can do. Right. You can clearly see this is the first three terms are the quadratic approximation and the fourth term is the error term. So whatever we have done in the linear approximation, Taylor's theorem for linear approximation, we will do the same things here also, but we have to compute more. That's the only challenge here. Our approximations will be better, but the computation part of the time it takes to compute will be more. Okay. Again, the same thing. So we want the second order Taylor approximation for f around x is equals to 1 means we are not worried about the error. All we need is q of x. And for q of x, all we need is these three things. Okay. So for that, already we have f of x. We need f prime of x to get f prime of a. And we need f double prime of x to get f double prime of a. Right. And before you start problems on this Taylor's theorem, you have to identify what is this a. Okay. So that's the starting point. So identify at which point you are asked to compute the Taylor's approximation. Okay. So look at that. So here they have asked us to compute the second order Taylor approximation around x is equals to 1. Right. So for that, x is from there you can see that a is 1. So once A is 1, we have to find f prime of 1, f double prime of 1, f of 1. Right, f prime of x is 1 by 2 root x plus x. And then f double prime of x is minus 1 by 4x power 3 by 2 plus 1. Right, so from here, f prime of 1 is 3 by 2 and f double prime of 1 is 3 by 4. Right, and f of 1 will be 1 plus 1 by 2, again 3 by 2.
3 by
So
2.
once we have these three terms, all we have to do is to write down q of x. Q of x is 3 by 2 plus 3 by 2 into x minus 1 plus 3 by 4 by 2 factorial. So don't forget, in a hurry, we will forget this 2 factorial into x minus 1 whole square. That's it. This is what q of x is. And this is what they have asked in the first part. For the second part, using Taylor's theorem, find an upper bound on absolute difference between f of 2 minus q of 2. Right? Again, upper bound or maximum possible error, everything is the same. Okay, so this will be, just hold on guys, my power is really low. Yeah. Sorry for that. So for bounding, this all we have to do is to compute the maximum possible error. Okay, so f of 2 minus q of 2, the maximum is bounded by this expression, right? So maximum of x3. So this is the error term. Okay, x2. And here also x2. Okay, whatever. So x2 in this interval, in the interval from 1 to
1 to 2.
1 to 2. Right, so x, here x is 2. And f double prime, oh no, f triple prime of x2 divided by 3 factorial into x minus a whole cube. Right, here x is 2, a is 1. So if you substitute it, we'll get maximum value of f triple prime of x2. We have to compute that, but this is 6 into 2 minus 1 whole cube. Right, so if you just scroll up, we have f double prime of x to be this. So from this, we have to compute f triple prime of x. So if I compute f triple prime of x, okay, so that we'll do it here. F double prime of x we have as 1 minus 1 by 4 into x power 3 by 2 plus 1. So from here, if I take the derivative once again, I'll have 3 by 8 into x power 5 by 2. So you can solve this. You just have to take the derivative of the above expression and you will obtain this 3 by 8 into x power 5 by 2. You can substitute it here. Maximum value of in the interval 1 to 2, and this is 3 by 8 into x2 whole power 5 by 2 and whole divided by 6 into 1. This and this will get cancelled out, and 8 2 is 16 and that will go out. So 1 by 16 into max of x2 in the interval 1 to 2, and the expression is again 1 by x2 power 5 by 2. So it is similar to 1 by x2 square, right? So the power is greater than 1 and it is in the denominator. And in this interval, you can clearly see that as
Sir, 6 is
x2,
multiplied by 3, no?
sorry,
6 is multiplied by 3. You have divided.
x is multiplied by 3.
No, it says 6 is multiplied by 3 in this expression. You cut the 3 and 6 by 2.
No, right? So this will be in the numerator. This whole thing is in the numerator and 6 is in the denominator.
It's correct, sir. Yes, sir.
Yeah, sorry, sir.
Yeah. So yeah, it is quite possible that you may think that 6 may go up, but that's not how the expression is actually. So the whole this thing is in the numerator and this is in the denominator. Okay, so it will cancel out. And 8 comes to the denominator. 8 times 2 will become 1 by 16. That will go out. And then if you see here, again we have reached the same kind of expression where our x2 is in between 1 to 2 and the expression is 1 by x2 whole power 5 by 2. Here also you can clearly
Get
see that the
maximum value
maximum
at
will be
1.
attained at, sorry
1.
Amit, 1.
Yes, sir.
So at 1 the value is 1 and anything else if you choose 1.1 or 1.2 the value will be lesser than 1. So the maximum value that this expression could have is 1. 1 by 1 power 5 by 2 which is 1. Therefore an upper bound or the maximum possible error, you call it whichever way you want, but it will be equals to 1 by 16. Right? So that is how we will find an upper bound to the error or the maximum possible error. Okay, and this is how you find the approximations. If they ask you to compute the linear approximation, you just compute the linear approximation. If they ask you to compute the quadratic approximation, then you have to compute this. And after that, for error, you have to follow these steps. Identify what is x, what is a. Then after simplification, you will get one expression only in terms of x2. And look at that expression, how it is. Okay. And then decide at which point this attains maximum. And it's not at which point it attains the maximum. We have to take the maximum value actually. Right. So I hope you all know this. And we have used that only, right? So we didn't take, it attains the maximum at E, but we didn't take E. We took the value. Okay. All right. So I think these are some concepts you should definitely practice more problems if you want to score better in quiz 2. And this is only week 5 and 6. Okay, so we'll do week 7 and 8 on Friday. But till then, you can practice more problems related to week 5 and 6. And also, you start preparing for 7 and 8 also. Okay, Friday will be too late. You just prepare and come for the session. And then we'll also have a nice discussion. That will be the second revision session. And with that, we will close our revision sessions for quiz 2. Okay, so this I really have to check on this. We have given all the things to them. Let me check, okay?
Sir,
Yeah.
sir, also the lecture slides are also not yet uploaded for the week from the week 6 on the
Okay,
portal.
I will check on this. I don't know why it is getting delayed.
Sir,
I
can
will ask
you
them
share
to.
this revision session as well?
Yeah. See, after the session, we have been sharing it. I don't know what is happening. Let me check. Let me check, and I will upload all the files by today or at max tomorrow morning.
Sir, under which lecture slide or live
It
session?
will be under supplementary contents. Okay, so I hope supplementary contents are not updating properly. I will take a look at it. Under supplementary contents, you will have the lecture slides, these live session notes,
Yeah.
and the practice and graded assignment solutions. Okay.
Yeah.
Okay, guys. So with that, I think we have come to the end of this session. So prepare well, and I hope you guys do great in quiz 2. You have done good in quiz 1. Let's continue that trend. We'll do better in quiz 2 and the best in enter. Yeah.
Okay, thank you, sir.
Sir,
Yeah. Thanks a lot.
sir,
Yeah. Yeah.
Sir, I have just one request, sir. Can you go through the question number 10 of mock? I think there is some ambiguity in the options.
Just a second. Let me open that. Okay.
Okay,
Okay.
sir.
Before that, let me stop the streaming.
Yes, sir.
Yeah. So others you can leave. Thanks all for